Hello, so today we will be going over some statistical modeling. We'll be looking at hypothesis testing, correlation coefficients, some linear models, and some assumptions associated with those models. So jumping right in, we'll have a hypothesis test, testing if there is a mean weight difference between males and females. So as you can see, loaded that data in, designated genders, male and female. I'll be using a t-test to test the hypothesis that there is no significant difference in mean weight between males and females. And as we calculate that, we'll also see a histogram to show if there's any significant difference or not. So our p-value here is very small, very, very small actually, and it is less than our significant value, our p-value of 0.05. So we must reject the null hypothesis. There is indeed a significant difference in the mean weight between males and females. And as we look at this histogram, we do see that there is only a slight overlap here in the middle. There is still a huge difference on each side for male and female. So that confirms that there is a statistical difference as well. Next, we'll do a correlation coefficient between height and weight. Use the Pearson correlation coefficient. And we'll also see it on a scatter plot. So the correlation coefficient is 0.7173. That means there's a high correlation, a very strong positive correlation between height and weight. And as we look at the scatter plot, we can see that actually there is a positive correlation. As height increases, so does weight, and vice versa. Next, we look at a linear regression model, and we're predicting weight based on height. So height is our independent variable, and weight is our dependent variable. We add our intercept in, and we do our linear regression model. And we also use the Shapiro-Wilk test to test for normality. And we'll see that visualization, as well as we'll do some residual analysis to check for heteroscedasticity. Hopefully I'm saying that right. So as we look at the ordinary least squares regression results, there's a lot of things on here. Based on this example, we're only going to look at a couple of things. We're going to look at the Durbin-Watson measurement as well as the conditional number. We see that Durbin-Watson checks for normality, and this score ranges from 0 to 4, and 2 meaning, actually, Durbin-Watson actually checks for auto correlation. Yes. And conditional number, it actually checks for multicollinearity. So the Durbin-Watson number is between 0 and 4, 2 meaning there is no auto correlation, 2 meaning there's no autocorrelation, and this is a little less than 2, but still kind of close. So this shows just a little negative or positive autocorrelation. The conditional number is used to check for multicollinearity. It's over 30, so that means that there is going to be some multicollinearity here. As we look at the Shapiro-Wilk test for normality, that p-value is smaller than our p-value, so that says that there is it's not necessarily distributed normally, the residuals. As you can see here, there's some residual here on the right that is skewed. And when we check for heteroscedasticity, it is scattered evenly around y equals 0, so it is fitted well. So again, the autocorrelation is close to 2 from that Durbin-Watson statistic. So that means there's slightly positive autocorrelation. That multicollinearity based on a conditional number is greater than 30. So that means that multicollinearity is present. For the normality, again, the Shapiro-Wilk p-value is less than 0.505. So there is, the residuals are not normally distributed. And lastly, heteroscedasticity, the residuals are evenly spread out along the y=0 axis. So we actually achieve homoscedasticity, this particular regression model. Next, we'll look at a multiple regression model to predict weight based on height and age. So height and age are our independent variables, weight is our dependent variable, and we print that model out using our ordinary least squares. We'll use that Shapiro test again and the analysis for residuals, checking for heteroscedasticity, and we'll visualize that as well. So again, looking at the same Durbin-Watson autocorrelation, it is closer to 2, so that means there's less autocorrelation than before. This conditional number is still greater than 30, so that means there is still multicollinearity in the multiple regression. Shapiro-Wilk's test shows that the p-value is less than 0.05, so the residuals are not normally distributed. So again, looking at that heteroscedasticity, it is normally distributed around or scattered around the y-axis here. So it means it's well fitted, and it's homoscedastic. Looking at the histogram or normality, again, we see that it is right skewed. So there is not necessarily a normal distribution of residuals. Question number 5 is about identifying 2 common assumptions of linear regression models. And again, you've heard about homoscedasticity and normality, but homoscedasticity is the assumption that the residuals have constant variance, and that the regression model is well fitted. We use a scatter plot to kind of visualize that and make sure that they're scattered evenly. If there is a funnel or a curved plot, then that indicates heteroscedasticity. Normality is the assumption that the residuals are distributed normally, and that we can use the predictions and confidence intervals, they're reliable. I've been using that Shapiro-Wilk's test to and visualizations of the histogram to see normality. And we can use a logarithmic transformation to kind of solve for those assumptions. So here I created a sample. I created a set of data here to make it heteroscedastic based on experience, age, and salary. So experience and age are going to be our independent variables, with salary being our dependent variable. And we're going to check for heteroscedasticity, which I made sure that it did. And we're also going to see it visualized. So here is a funnel indicating heteroscedasticity. The other ones we have seen have been homoscedastic because they were evenly distributed, but this one is actually a pretty clearly defined funnel. So I'll use logarithmic. I also plotted the normality, but I'm just going to focus on the heteroscedasticity and correcting that. So I use a logarithmic transformation And again, I go back and plot those after the logarithmic transformation. I did that here and go back and see the residuals plotted. And as you can see here, it actually changed from a funnel shape to much more closely around the y-axis. So that eliminated some of that heteroscedasticity. It's still a slight curve, but not much. And that was not the best option for normality. So it did solve for the heteroscedasticity, but not necessarily for the normality. And last, we're going to look at a nonlinear model. So that same data set of experience, age, and salary. I'm doing another logarithmic transformation on the entire data set. And we're going to look at that as well. And as you can see, it does still have some heteroscedasticity. However, it is a little more fit, but there is some heteroscedasticity here. As you can see those outliers here. The normality is a little more of a bell shape, but we still have this right skew here, which means that some of the residuals are overestimated. So that's a look at statistical modeling.